All right, today we're diving into a classic coding interview question, but one with a really, really clever solution. We're going to break down how to check for a palindrome using this cool technique called two pointers. Let's jump right in.
Okay, so take a look at this famous sentence. Right away, your brain just knows it's a palindrome. But how would you get a computer to see that? You can't just reverse it, right? Because you've got spaces, a comma, a colon, not to mention the different cases, like that big A at the start and the little a at the end. That's the real puzzle we have to solve.
So, just to make sure we're all on the same page, what even is a palindrome? Super simple, right? It's just something that reads the same forwards and backwards. Like madam or race car. The tricky part is applying that simple idea to a messy string like the one we just saw. Here's the game plan for this explainer. First, we'll really dig into the puzzle itself. Then we'll look at a common kind of brute force idea before we unveil the much smarter two-pointer solution. After that, we'll actually trace the pointers to see how they work. And finally, we'll talk about why it's just so darn efficient. All right, so let's get into our first section, the palindrome puzzle. Because as we said, this is about way more than just reversing a string. The real challenge here is filtering out all that junk, the spaces, the punctuation, all the non-alphanumeric characters, and then comparing only the letters that matter without worrying about whether they're uppercase or lowercase. Okay, so when you face a problem like this, what's the first thing that pops into your head? Probably something like, well, if the extra characters are the problem, why don't we just get rid of them? And that's exactly what the brute force approach does. It's a totally logical first step, but as we'll see, it's got a hidden cost. So how would you do that? Well, the steps are pretty straightforward. You'd probably start by creating a brand new empty string. Then you loop through the original one character by character. If you see a letter or a number, you just grab its lowercase version and stick it into your new string. By the end, you've got this nice, clean string like Anne, Mana, Pla, Canal, Panama, which is super easy to check. But here's the catch, and it's a big one. Creating that brand new string, it's kind of like photocopying an entire book just so you can read it backwards. It takes up extra space in your computer's memory. Now, if the original string is just a short phrase, who cares, right? But what if it's a whole book? Suddenly, you're using twice the memory. In the world of programming, that kind of inefficiency really matters. And it's exactly what leads us to a much, much smarter way to do this. And that brings us to the real star of the show today, the two-pointer solution. This technique is honestly just brilliant. Why? Because it completely avoids creating a new string. It does all the work directly on the original, messy input. Let's put these two ideas side by side so you can really see the difference. The clean first method needs more and more memory the longer your string gets. We call that O of n space complexity. But the two-pointer method, it uses the same teeny tiny constant amount of memory, whether the string is 10 characters long or 10 million. That's what we call O of 1 space complexity, and trust me, that is a huge, huge win. The absolute genius of this method is right here. It skips the junk in place. There's no separate cleanup step, no pre-processing needed. It just deals with the junk characters as it goes, on the fly. Okay, so how does this magic actually work? Well, imagine you place two fingers on the string, a left pointer right at the beginning and a right pointer at the very end. Now you start a loop. You slide that left pointer forward, hopping over any junk until it lands on a letter. You do the same thing with the right pointer, but you slide it backward. Then you stop and compare the two characters. If they match, awesome. You just move both pointers inward and do it all again. But if they ever don't match, you can stop right there. Game over. It's not a palindrome. And if your pointers eventually meet in the middle or cross over, then you've proved it is a palindrome. Simple as that. I know that might sound a little abstract, so let's make it super concrete. We're going to trace this process step by step using our famous Panama Canal sentence. Okay, here we go. Right at the start, our left pointer is sitting on that uppercase A, and our right pointer is all the way at the end on the lowercase a. The algorithm is primed and ready for its first comparison. First thing we do is compare their lowercase versions. Is A equal to A? Yes, it is. It's a match. So what do? We just move the left pointer one spot to the right and the right pointer one spot to the left. And now you get to see that on-the-fly cleaning in action. The left pointer hits a space, nope, skips it. Then it hits a comma, skips that too. No new string is being made. It just keeps moving until it lands on the M. Meanwhile, the right pointer, coming in from the end, also finds its way to the other M. So we compare again. M equals M. Perfect, another match. We move both pointers inward one more time. And this exact process, skip, compare, move, just keeps on repeating as our 2 pointers march steadily toward the center of the string. And eventually, after a whole bunch of successful matches, our pointers are going to meet or cross right in the middle. And because we never, not once, found a mismatch along the way, we can say with 100% confidence, yes, this string is a palindrome.
So we've seen that it works, which is great. But now let's really nail down why this algorithm is so powerful and take a look at how it handles some tricky situations.
The single biggest victory here is this: O of 1, or constant space complexity. We're not building copies of anything, we're just using 2 little variables to keep track of our left and right positions. That's it. It is incredibly light on memory. And what about this speed? Well, in the worst case, our 2 pointers combined are going to pass over every character in the string just once. That gives it what we call a time complexity of ON. So you really get the best of both worlds. It's fast, and it uses almost no extra memory.
You know, a good algorithm has to be tough, it has to be robust. And just look at how this one handles all these weird edge cases. What about an empty string or a string with just one character? Yep, it correctly says true. A string that's nothing but punctuation? Still true. It works perfectly with numbers and mixed case letters too. It's just solid.
And the reason it handles those empty or all junk strings so well is all because of that while left less than right condition in the main loop. For an empty string, the loop just never runs. For an all junk string, the pointers will just skip right past each other looking for a letter they'll never find. Since a mismatch is impossible, the function correctly returns true. We sometimes call this being vacuously true. So, this 2-pointer technique is a fantastic pattern to have in your toolbox for any problem that involves, working from the outside in. It's for way more than just palindromes. So, I'll leave you with this question to think about. Where else could you use this powerful idea of starting from both ends and meeting in the middle?